Okay, you remember the formula? Yeah. Yeah, so we're calculating limit of detection, right? It's just the background equivalent concentration, which is up here, right? Times 3 times the relative standard deviation, which is right here, divided by 100. And then you can just fill it across. Move it up here then. Okay. Did you get the same values that I did? So RSD are these values right here. It's right there. Yeah. And the units are milligrams per liter. Okay. Bless you. All right, you good? You want me to make it bigger? So then we have these values in parts per million or milligrams per liter. The other bit of information that we have is these calibrations, right? So the R squared for the calibration just tells us how close of a fit our data are to the straight line that we are trying to create for our calibration. The standards that we used are over here to do the calibration. So we did a calibration, we get these R squareds, and one of the things that we do initially is to calculate a limit of detection, right? Based upon the background equivalent concentration, these percent relative standard deviations. So these are all in milligrams per liter, and you can see that they're really small, right? So it'd be much more convenient to write these as a microgram per liter or as a part per billion. And so if we write them as parts per billion, what is going to be the value for the first one for calcium? 2.08, right? 2.08, we'll just do it to the hundredths place. For potassium, it'll be 24.48, right? And so what you can do then is take these values and put them into that table that I created. That table is, there it is right there. You know what I mean? In a good place? Yeah. Go ahead and do that. You have any questions? Good. You get similar values as me. Awesome. Right. Paige, is there a discrepancy? Is there a difference between what you got and what I got? 4. Magnesium is different. You got a value of 2.
Oh, I got the same thing.
You got point.
0.35.
All right. Well, let's see here. So is your formula for that one D5 times 3 times, oh, maybe that's my problem. D9. Okay. That's my think here. All right. I think that mine are incorrect. Let me do that again.
We don't get along. Figure out the number.
Didn't change.
It was 0.345 instead of 3.45, which is one place. The decimal is just one place over.
Decimal is just one place over. So are you saying, Lee, that mine's wrong? You are.
Yeah, I mean, we got the same thing. Oh, because for the BEC value, it's 0.03.
Right here. So I copied it wrong.
You retyped it with me.
Oh, yeah. And you did better. There we go. So
Yeah.
that value then should be 0.35 for our 0.35. All right. Good. Okay. So next thing that we're going to do is go to our other spreadsheet because we're going to look at the method detection limit now. Because every single value after the instrument detection limit, or every single value that we get, is based upon it went through the method. So the lowest levels that we can determine for anything are based upon what the method detection limit is. Okay. So cations for ECEC is the table that I'm going to, or the worksheet that I'm going to be looking at here. And the specific values are all related to the method blank here. Right there. Okay. So what I'm going to do is I'm going to insert like, yeah, let's do this. Yeah. What I'll do is I will insert like 5 lines here. Okay. And I'm gonna just to make it so we're bracketing our method values, I'm gonna do a few lines up at the top too. Right, just so they're separated from everything else. But I made a slight mistake. Do that. Okay. So the method detection limit is the lowest level that we can detect using the method that we used. And the method detection limit is going to be unique for each element. And it is also a formula. And the formula this time is based upon the student t-test. You remember. The slides for method detection limit are here. So that's our method detection limit formula. Right, we got the average of all the blanks plus standard deviation of the blank times student t-test alpha of 0.01. Okay, so first thing that I want to do is I want to calculate the average. And I'm going to calculate the standard deviation, and then I'm going to multiply that by the student t-test alpha of 0.01. And we ran 10 blanks. And if we look at the student t-test for 10 blanks, alpha of 0.01 is here, right? And the student t-test for how many degrees of freedom? 9 degrees of freedom, right, is here. So our value is going to be this one, 2.821 is the one that we're going to use, right? So going back to the spreadsheet, there it is there. So I'm going to first calculate the average. And then I'm going to calculate the standard deviation. The standard deviation you want to use is the one that's std.p, standard deviation of the population. And then from there, we'll be able to calculate a method detection limit. Right. So for our average value, you can just plug in the formula. You can do the standard deviation also the same way. It's if you look at the formula, it's stdev.p is the acronym that they use. Yeah, here you go.
We also go. Towards
What do you mean by that?
your insert those calculations after whatever. Sorry.
Okay.
What's the equation for the STDP?
The equation for STDP is like it has the formula built in. So the acronym that they use is stdev.p, and it's just standard deviation. It's just calculating standard deviation of that population. So then what you can do is you can take these values that we just calculated for the method detection limit, and I'll make it bigger. Right, these values here, they are all in milligrams per liter, and you can plug them into the table. Right, this is calcium, potassium, magnesium, sodium. They go in table 2. Glad you. What do you notice about our method detection limits? How do they compare to our instrument detection limits? A lot higher, right? Orders of magnitude higher. What about sodium? Sodium's really high, right? Which suggests that you might be having some contamination or some kind of interference from somewhere. And I don't know if you remember me saying this, but it turns out that the sodium is artificially elevated because within the filter paper, there's leachable sodium. And we discovered that over time because our sodium values have always been really high or higher than we would expect. And so we ran blanks to figure it out that was the case. So what we're going to do is we're going to take our average values, and we're not going to use our method detection limit, but we're going to take our average values and subtract these from all of our other values when we do the calculations for CEC and stuff like that. Okay, so for now, somewhere, just go ahead and write that down. What your values are for calcium, potassium, magnesium, and sodium, and we want the average values. So our time is done, but what we're going to do on Thursday is we're just going to continue to work through our data. So we have no experiments planned. It's just going to be talking through the data and doing more calculations. And secondly, and what was I going to say? Oh yeah, make sure that you have Jump installed on your computer and that you can open it. So it's one thing to install it, and it's another thing to be able to open it. So make sure that you can open it and use it. Yeah, Lee, and then
For this table, do we need this to be in our report or the method?
Oh. that you're turning in.
Yeah.
Great question. No. Yeah. So for what you're turning in on Thursday, you don't need to have any QC information yet. We'll get that on the next go around.
For Jump, I was able to speak in like trying to figure out how to install stuff. And I was like able to get